We have spent decades shouting into the infinite, hoping against all mathematical probability that the void would answer back. We built metal ears the size of stadiums and left them listening to the dead static of ancient radiation. We launched mirrors of beryllium covered in microscopic layers of gold to float 1 million miles from Earth, freezing in the permanent shadow of our planet. All to catch a ghost, a single stray photon that originated centuries ago, carrying the faintest barcode of chemistry from a world we will never touch. For all of human history, the results have been exactly what a cold, indifferent universe promised us. Absolute, deafening zero. Until now. In the vast catalogue of exoplanets, there is an unspoken rule among astronomers. Data is messy, atmospheric readings are ambiguous, and certainty is a myth. When we analyze the starlight filtering through the razor-thin atmosphere of a distant world, we look for absorption lines. We look for the missing colors in the spectrum, swallowed by gases like methane, carbon dioxide, or dimethyl sulfide. Usually, the signals are faint whispers buried in immense cosmic noise, a 50% probability of water vapor, a 60% chance of localized methane. We debate, we publish, and we wait for better instruments. But recently, the telemetry downlinked from the James Webb Space Telescope did not return a whisper. It returned a siren. The atmospheric data from a rocky world sitting squarely in the habitable zone of a relatively close star yielded a biosignature confidence level of 99.7%. In the rigorous, unforgiving discipline of astrophysics, 99.7% is not a statistical anomaly. It is not an instrument calibration error, a glitch in the sensor array, or a trick of stellar flare activity. It is a mathematical certainty. It means the light passing through that alien atmosphere carries the undeniable fingerprint of a biosphere in an active, aggressive chemical imbalance. Gases that should instantly destroy each other are existing in massive quantities side by side, a state that cannot be sustained by geology or volcanism alone. Something on the surface of that planet is metabolizing. Something is manufacturing that atmosphere faster than the stellar winds can strip it away. We are no longer alone. And suddenly, the empty, quiet universe feels incredibly crowded. If you are drawn to the terrifying beauty of the cosmos, if you demand to understand the mechanics of the void without the comfort of illusions, subscribe to this channel and join us in the dark. We are about to look closer at the raw telemetry, the numbers that keep astrophysicists awake at night. Because a 99.7% signal does not just answer our oldest philosophical question, it triggers an entirely new, infinitely more dangerous one. To understand the terrifying gravity of a 99.7% biosignature, we must first violently dismantle a fundamental human delusion. Since the dawn of our species, we have looked up at the night sky and trusted our eyes. We built an intuition based on the simple mechanics of human vision. You look at an object, light bounces off it, and your brain paints a picture of reality. When we built our first telescopes, we merely scaled up this primitive biological mechanism. We ground glass into massive lenses to magnify the distant dark, expecting to see mountains and valleys on other worlds, hoping to eventually zoom in close enough to see the alien cities, the oceans, the foreign clouds. But the universe does not allow for such simple voyeurism. The distances involved in interstellar space are so violently vast that they break the very geometry of optics. You cannot simply build a bigger magnifying glass to look at an exoplanet. The closest star system to our own is over 4 light-years away. To put the brutal mathematics of that distance into perspective, if the Earth were a single grain of sand, the nearest star would be another grain of sand over 20 miles away, and between them is nothing but a freezing, lethal vacuum. By the time the light from a distant solar system reaches our orbital neighborhood, the photons have been traveling for decades, centuries, or millennia. They are exhausted, scattered, and overwhelmingly drowned out by the blinding nuclear furnace of their host star. Trying to directly photograph an Earth-sized exoplanet orbiting a distant sun is not like trying to see a firefly next to a searchlight. It is like trying to see a specific moth fluttering near a nuclear detonation from 1,000 miles away through a thick fog. Our intuition tells us that seeing is believing. But in modern astrophysics, direct observation is a dead end. We do not look at exoplanets. We never have. We observe their shadows and we dissect the ghosts of the light they intercept. This counterintuitive leap, the foundation of how we currently decode the cosmos, did not begin in the modern era of spaceflight. It began in the early 19th century with a Bavarian glassmaker named Joseph von Fraunhofer. While testing prisms, Fraunhofer decided to direct his lenses toward the brightest object in the sky, our own sun. When he spread the sunlight into a rainbow spectrum, he did not see a continuous, perfect smear of colors. Instead, his optics revealed something deeply unsettling. The solar spectrum was scarred. It was riddled with hundreds of thin, pitch-black lines, like a celestial barcode stamped across the light. Fraunhofer had no idea what he was looking at. He meticulously mapped these dark voids, documenting their exact positions across the color spectrum, completely unaware that he had just handed humanity the master key to the universe. It took decades for quantum physics to catch up to Fraunhofer's glasswork and explain the dark lines. The explanation shattered the ancient philosophical belief that the heavens were made of some ethereal, unknowable substance. The black lines were missing photons. They were specific wavelengths of light that had been swallowed alive by the atoms in the sun's outer atmosphere. The mechanics of this process are cold, quantum, and flawless. Every element in the periodic table, from the lightest hydrogen to the heaviest iron, has a unique atomic structure. Electrons orbit the nucleus in strictly defined energy levels. When a photon of light travels from the core of a star and passes through a gas, it will pass right through undisturbed unless its energy perfectly matches the gap between an electron's orbits. If the match is perfect, the atom absorbs the photon. The light dies in that exact microfraction of the spectrum. Therefore, when we look at the light of a star through a prism, the black lines tell us exactly what elements the light had to pass through to reach us. We are not looking at the light. We are looking at the autopsy of the light. We are reading the chemical shadows left behind by the gas. This is the science of spectroscopy. It is the realization that the universe can be entirely understood not by what is visible, but by what is missing. For over a century, we used spectroscopy to analyze the burning atmospheres of stars and the chaotic expanding clouds of nebulae. But the real ambition, the silent obsession of the astronomical community, was to turn this technique toward the infinitesimal rocks orbiting those distant stars. We wanted to pass starlight through the atmosphere of an alien planet and read its chemical barcode. The engineering required to achieve this borders on the impossible. First, you must find a planet that happens to be perfectly aligned with our line of sight to its star. The vast majority of planets orbit at angles that we can never observe. We can only detect the ones that transit, the ones that pass directly between our telescopes and their sun. When this happens, the star's brightness drops by a microscopic fraction. The mathematics of a transit dictate a brutal reality. The drop in the star's luminosity is proportional to the square of the planet's radius compared to the star. For a rocky, Earth-sized world crossing a sun-like star, the dimming is less than 1/100th of 1%. It is a shadow so slight, so ephemeral, that detecting it requires staring unblinkingly at a patch of sky for months, waiting for a localized pixel of light to dim for just a few hours. But finding the planet is only the prologue. The true terror of the engineering comes in the next step. During that transit, as the planet silhouetted against the blinding nuclear fire of its star, a tiny, almost negligible fraction of that starlight skims through the very edges of the planet's atmosphere before continuing its journey across the galaxy to us. That microscopic sliver of filtered light carries the absorption lines, the chemical barcode of the alien world's air. To catch that barcode, you cannot use a telescope sitting on the surface of the Earth. Our own atmosphere is a thick, chaotic soup of water vapor, nitrogen and oxygen. It heavily absorbs starlight, scrambling the signal. Trying to read the delicate atmospheric signature of an exoplanet through Earth's atmosphere is like trying to listen to a whisper from across a room while standing next to a screaming jet engine. You have to leave the planet. This is why we built the James Webb Space Telescope. It is not merely a camera. It is a $10 billion cryogenic spectrograph designed to operate in the most hostile environment imaginable. We launched it 1,000,000 miles away from Earth to a gravitational parking spot known as Lagrange Point 2. Out there, it sits in eternal isolation, far beyond the reach of any human repair mission. It is entirely alone in the dark. But distance from Earth is not enough. The universe is ancient, and because space itself is expanding, the light from distant objects gets physically stretched as it travels through the void. By the time ancient starlight reaches us, its waves have been stretched out of the visible spectrum and into the infrared. To see this light, James Webb must detect heat, and to detect the faint, ghostly heat of a distant transit, the telescope itself must be colder than anything in nature. It deploys a sun shield the size of a tennis court, made of 5 microscopic layers of kapton, to block the blazing heat of the sun, the Earth, and the Moon. Behind this shield, the mirrors and the scientific instruments plunge into a deep freeze of near absolute zero. The mathematics of its thermal management are terrifying. The sun-facing side of the shield boils at over 200 degrees Fahrenheit. Just feet away on the dark side of the shield, the instruments operate at -400 degrees Fahrenheit. The slightest tear in that shield, a single micrometeoroid strike in the wrong place, and the telescope's own heat would blind its sensors instantly, turning the greatest feat of human engineering into useless space debris. Webb uses its massive gold-coated beryllium mirrors to gather the infrared photons, focusing them into spectrographs that slice the light into a high-resolution barcode. It captures the light that scraped through the atmosphere of the distant planet, isolates it from the blinding glare of the host star, and looks for the missing lines. It looks for the shadows of molecules. When we process this data, we are looking for a very specific type of chemical architecture. We are looking for something that breaks the fundamental laws of thermodynamics. In a dead universe, chemistry is a one-way street toward equilibrium. Left to its own devices, a planetary atmosphere will chemically react with itself, bond, and settle into a stable, inert state. Mars is a dead world. Its atmosphere is mostly carbon dioxide, entirely stable, chemically exhausted. Venus is a hellscape, but it is a stable hellscape, locked in a permanent equilibrium of thick carbon dioxide and sulfuric acid. If you leave a mixture of gases alone for millions of years, they will find their lowest energy state and stop changing. But Earth is an anomaly. The Earth's atmosphere is wildly, violently unstable. It is a volatile mixture of oxygen, nitrogen, methane, and carbon dioxide. Oxygen is a highly reactive gas. It wants to bond with everything. It rusts iron, it feeds fire, and it quickly bonds with methane to form carbon dioxide and water. Thermodynamics dictates that the methane and oxygen in Earth's atmosphere should have annihilated each other millions of years ago. They cannot naturally coexist in large quantities for any geological length of time. And yet they do. They are constantly present. The only way to maintain this massive planetary-scale chemical disequilibrium is if something is continuously manufacturing and pumping millions of tons of these reactive gases back into the sky, faster than they can destroy each other. On Earth, that violent, non-stop engine of atmospheric instability is biology. It is the forests, the oceans, the bacteria, the living, breathing, dying organisms that constantly vomit reactive gases into the air, keeping the atmosphere in a permanent state of chemical tension. When astrophysicists point the James Webb Space Telescope at a distant exoplanet, they are not looking for radio signals. They are not looking for geometric megastructures or the exhaust of alien starships. Those are the fantasies of science fiction. The cold reality of the hunt is much more insidious. They are looking for an atmosphere that refuses to die. They are looking for gases that are locked in a violent thermodynamic struggle, existing together when the cold math of chemistry says they should not. They are looking for a planetary-scale engine of disequilibrium. For years, the atmospheric readings we gathered from exoplanets were noisy, filled with static, and mathematically inconclusive. We saw hints of water vapor. We saw the potential for carbon compounds. But the error bars were massive. A reading might suggest the presence of a biosignature gas, but the confidence level would hover around 50 or 60%. In the harsh light of scientific peer review, 50% is nothing. It is a coin toss. It is atmospheric noise easily dismissed as a localized volcanic event or a bizarre photochemical reaction triggered by the host star's radiation. The universe is incredibly skilled at mimicking life through strange, dead geology. We learned to temper our expectations, to accept that the void would only ever offer us ambiguous shadows. But then, the mirrors of the James Webb locked onto a target in the habitable zone of an unassuming red dwarf. The spectrographs began to dissect the light, capturing the infinitesimal dip in the infrared spectrum as the planet transited. The data was downlinked, transmitted across 1,000,000 miles of empty space, unpacked by supercomputers on Earth, and run through the complex algorithms designed to filter out the noise. The resulting atmospheric spectrum did not show a hint. It did not show an ambiguous, noisy curve that could be argued over in academic journals. It showed a sheer, aggressive drop in the specific wavelengths corresponding to a cocktail of highly reactive, incompatible gases. The absorption lines were carved into the data with a depth and clarity that defied every standard model of planetary geology. The statistical analysis was run again and again. The algorithms checked for instrument calibration errors, for thermal bleeding, for stellar flare interference. The mathematics held. The confidence interval did not collapse back into the noise. It sharpened. It locked in at a number that sent a cold shockwave through the control rooms and the closed-door meetings of the astrophysics community. 99.7%. The light from that distant world is screaming. It is carrying the unmistakable, mathematically verified shadow of a planetary atmosphere in a state of absolute, chaotic disequilibrium. Something down there, beneath those alien clouds, is breathing. But as the sheer scale of this discovery begins to settle, as the champagne remains uncorked and the scientists stare at the raw data, a new creeping dread begins to take hold. Because understanding the sheer volume of gas required to produce a signal, this dominant forces us to look closer at the mechanics of that distant world. And the more we look at the scale of what is happening, the sheer volume of gas required to produce a signal, this dominant forces us to look closer at the mechanics of that distant world. And the more we look at the scale of what is happening, the more the illusion of a peaceful, Earth-like alien paradise shatters into something far more violent and unforgiving. To comprehend the magnitude of this 99.7% biosignature, we must first understand the brutal real estate upon which this planetary engine operates. The host star of this system is not a yellow dwarf like our Sun. It is an M dwarf, commonly known as a red dwarf. In the stellar census of our galaxy, red dwarfs are the silent, overwhelming majority. They make up roughly 75% of all the stars in the Milky Way. When you look up at the night sky, you cannot see a single one with the naked eye. They are too small, too dim, and too cold to broadcast their presence across the interstellar gulf. Our own Sun operates through a complex internal structure of radiation and convection, but a red dwarf is essentially a fully convective sphere of boiling plasma. Because of their low mass, the nuclear fusion at their core burns at a fraction of the rate of our Sun. A star like this does not burn out in billions of years, it burns for trillions. Every red dwarf that has ever formed in the history of the universe is still shining today. But this longevity comes with a devastating catch for any planet in its orbit. Because the star is so dim, the habitable zone, that narrow orbital band where temperatures allow liquid water to exist on a planetary surface, is dragged incredibly close to the stellar fire. To stay warm enough to support liquid oceans, a planet around a red dwarf must orbit at a fraction of the distance between Mercury and our Sun. It is a suffocating embrace. And when a planetary body of rock and iron is forced to orbit that intimately with a massive gravitational anchor, the laws of orbital mechanics exact a terrible toll. It triggers a phenomenon known as tidal locking. The physics of tidal locking are inescapable. Gravity is not a uniform force, it stretches and pulls. As a planet orbits close to a star, the immense gravity pulls harder on the near side of the planet than on the far side, warping the solid rock into a slight oval shape. As the planet rotates on its axis, this gravitational bulge is constantly being dragged back and forth across the planet's crust. This creates internal friction, an immense, invisible drag that acts as a planetary brake. Over millions of years, this friction bleeds away the planet's rotational momentum until it simply stops spinning relative to its star. The consequences of this mathematical inevitable are apocalyptic. The planet becomes locked in a synchronous orbit. One hemisphere faces the eternal unblinking fire of the red dwarf. The other hemisphere is cast into a permanent, freezing night, staring out into the absolute zero of the cosmic void. There are no days. There are no nights. There are no seasons. The passage of time is measured entirely by geography. If you were to stand at the substellar point, the exact center of the day side, the alien sun would be locked directly overhead forever. The radiation beating down on this point would be merciless, driving the surface temperatures to boiling extremes, creating a permanent, localized hurricane of rising, superheated air. Conversely, the anti-stellar point on the dark side is a realm of eternal midnight, where temperatures plummet so violently that the atmosphere itself should freeze into solid snow, locking away carbon dioxide and water in vast, dark glaciers of dry ice. According to traditional planetary models, a tidally locked world should be a dead world. The extreme temperature differential should either boil the oceans away into space on the day side or freeze the entire atmosphere onto the surface of the night side, leaving a barren, airless rock. Yet the telemetry from the James Webb Space Telescope dictates otherwise. The absorption lines are clear, defiant, and mathematically unyielding. Not only does this planet have an atmosphere, but that atmosphere is saturated with a chemical compound that demands a sprawling, hyperactive biological engine. The data does not merely show methane or oxygen. The spectrographs have isolated the intricate, deeply complex shadow of a molecule closely resembling dimethyl sulfide. In the cold, unfeeling realm of astrochemistry, this specific molecular arrangement is a smoking gun. You can find methane on the dead moons of Jupiter. You can find carbon dioxide on the frozen deserts of Mars. These are simple molecules, easily forged by the blind geological crushing of rock and heat. But a molecule like dimethyl sulfide requires an architecture of construction that defies random chance. It is a heavy asymmetrical assembly of carbon, hydrogen, and sulfur. On Earth, you will not find this gas leaking from a volcano. You will not find it reacting out of a lightning strike in a primordial soup. In the entire catalogue of our planet's complex chemistry, dimethyl sulfide is produced exclusively by life. Specifically, it is the metabolic exhaust of marine phytoplankton floating in the upper layers of our oceans. It requires cellular machinery, genetic encoding, and a biological imperative to exist. Finding the spectral signature of this molecule in the atmosphere of an exoplanet is the equivalent of finding a manufactured microchip buried in a layer of prehistoric bedrock. It does not belong to the world of dead rocks. It is the footprint of a biological factory, but the true terror of the discovery lies not in the mere presence of this gas, but in the overwhelming scale of the signal. The mathematical depth of the absorption line captured by the telescope's infrared sensors indicates a concentration of this biological exhaust that vastly eclipses anything produced on Earth. To achieve a 99.7% confidence level over a distance of dozens of light years, you are not looking at a few isolated pockets of bacteria clinging to a hydrothermal vent. The physics of atmospheric dispersion mean that for the telescope to see a shadow this dark, the gas must be globally saturated. The entire alien atmosphere must be choked with it. Consider the sheer mass required to maintain this level of atmospheric density. On Earth, our oceans cover 70% of the surface and teem with billions of tons of biomass. Yet the chemical traces they leave in our total atmospheric volume are relatively faint, often measured in parts per million or billion. To generate the profound spectral dip recorded by the Webb instruments, the biological engine on this exoplanet must be operating at an industrial, almost violent level of overproduction. This forces astrophysicists to model the fluid dynamics of a world that shouldn't harbor life, yet clearly harbors an ocean of it. How does an ocean survive on a planet caught in a permanent tug-of-war between fire and ice? The answer lies in the narrow ribbon of twilight that separates the two extremes. It is the Terminator line. Between the boiling desert of the eternal day and the frozen wasteland of the endless night, there exists a borderland. In this zone, the red sun sits perpetually on the horizon, casting infinite shadows across an alien sea. But this is not a peaceful sunset. The extreme temperature gradient between the two hemispheres creates a thermodynamic pressure vacuum of catastrophic proportions. The superheated air from the day side violently expands and rushes toward the freezing vacuum of the night side. This mechanism powers a global wind system that defies human comprehension. We are talking about permanent supersonic gales howling across the Terminator line, a ceaseless planetary jet stream tearing through the twilight. This atmospheric conveyor belt is the only thing keeping the planet alive. It acts as a massive thermal radiator, carrying just enough heat into the dark side to prevent the entire atmosphere from freezing and bringing just enough cold air back to the day side to prevent the oceans from entirely boiling into the void. The oceans themselves must be caught in this violent circulation. Immense oceanic currents, driven by the planetary winds and the extreme temperature disparities, would constantly churn the waters, pulling nutrients from the deep and dragging them across the twilight zone. It is in this chaotic churning borderland that the mathematics suggests the biological engine is running. But why is the signal so strong? Why would a biosphere produce such an overwhelming, saturated volume of this specific molecular exhaust? The answer forces us to confront the true, hostile nature of red dwarf stars. While they may burn long and cold, red dwarfs are magnetically chaotic. Because their internal structure is constantly boiling from the core to the surface, their magnetic fields are twisted and unstable. This instability frequently violently snaps, releasing stellar flares that dwarf anything our sun has ever produced. These flares lash out across the vacuum, bombarding the close orbiting planets with devastating tsunamis of X-rays and extreme ultraviolet radiation. For decades, this was the primary argument against life around red dwarfs. The math suggested that these violent stellar outbursts would strip away a planet's ozone layer, violently break apart water molecules, and sterilize the surface with lethal radiation. A habitable zone around a red dwarf was considered a theoretical illusion, a place where water might exist, but biology would be continuously annihilated by the angry host star. Yet the towering 99.7% signal demands a reconciliation between the lethality of the star and the undeniable presence of life. The saturation of the biological gas is not merely a byproduct, it is likely a mechanism of survival. When biologists and chemists run simulations of hyperactive biological systems under extreme radiation stress, a terrifying theory begins to emerge. The organisms in that turbulent twilight ocean are not merely surviving the radiation, they might be feeding on it or desperately shielding themselves from it. The massive overproduction of complex sulfur compounds could be a planetary-scale defense mechanism. By pumping millions of tons of this heavy gas into the upper atmosphere, the alien biosphere might be actively constructing a chemical smog, a sacrificial layer designed to absorb the brunt of the stellar flares before they can penetrate the ocean surface and shred their genetic material. If this model holds true, we're not looking at a delicate, fragile ecosystem struggling to hold on. We are looking at a hyper-aggressive, incredibly robust biological network that has industrialized its own atmosphere to survive a hostile star. It is a biosphere operating in a state of permanent, high-velocity biological warfare against its own sun. The oceans are not quiet. They are a massive, churning chemical plant, churning out billions of tons of protective exhaust, driven by supersonic winds and bathed in the flickering, angry light of a red star. The sheer vitality required to maintain this system over geological timescales is staggering. It implies an evolutionary ruthlessness that outpaces our own planet's history. On Earth, life was nearly extinguished multiple times by relatively minor volcanic shifts or asteroid impacts. But the engine on this distant world has locked into a stable, if violent, equilibrium with an environment that should be fundamentally lethal. As the supercomputers at the space agencies continue to crunch the raw telemetry, refining the spectral bands, and isolating the isotopic ratios of the gases, the physical picture of the planet sharpens. It is a world of immense, terrifying extremes. A frozen dark side hiding under glaciers of dry ice, a blinding, boiling dayside, and a ring of twilight oceans whipped by endless storms, choked with a biological smog thick enough to be seen across the interstellar void. This level of planetary engineering by microscopic or perhaps macroscopic biology breaks the boundaries of what we considered necessary for life. We spent our history looking for a second Earth, a quiet blue marble with gentle seasons and a stable yellow sun. We assumed that the conditions for life were fragile, a delicate tightrope walk of precise temperatures and calm orbital mechanics. Instead, the first undeniable whisper from the dark universe has come from a hellscape. It proves that life is not a fragile anomaly that requires perfect conditions to take root. It proves that biology, once sparked, is a relentless thermodynamic force. It will adapt to permanent twilight. It will adapt to supersonic winds. It will adapt to the lethal radiation of a volatile star. And it will multiply until it alters the very chemistry of its world, broadcasting its defiance into the void. But as the astrophysics community begins to accept the reality of this indestructible biosphere, a colder, much darker mathematical problem begins to surface in the orbital dynamics. The instruments on the James Webb are incredibly precise, but they are also bound by the strict laws of quantum physics and the speed of light. They can only tell us what is happening at the exact moment the light passes through the atmosphere. They cannot tell us what is happening beneath the oceans, and they cannot predict the long-term stability of a system stretched this thin. Because when you look at the raw mass of the planet, the orbital velocity, and the magnetic interference of the red dwarf, the equations that dictate the survival of this world begin to break down. The atmospheric pressure differential that sustains the twilight winds is not a permanent fixture. It is highly sensitive to the stellar output. And there is a fundamental paradox hidden deep within the absorption lines of the James Webb data, a conflict in the quantum chemistry that suggests this aggressive biological engine is not merely fighting its environment. It might be rapidly, uncontrollably consuming it. The numbers dictate that a biosphere operating at this level of overdrive under this specific gravitational strain triggers a thermodynamic chain reaction. And as we push the atmospheric models further into the future, simulating the next 1,000 or 100,000 years of this planet's existence, the outcome does not point toward a stable, enduring ecosystem. It points toward an invisible, impenetrable barrier in the physics of the planet itself, a wall that even the most aggressive life cannot adapt to. The data pouring in from the Lagrange point is immaculate, heavily scrubbed of interference, and mathematically unyielding, yet it forces astrophysics into a corner from which there is no easy escape. When a 99.7% biosignature flashes across the screens of our supercomputers, the immediate human instinct is to declare a definitive victory. We want to believe that the mystery of biological isolation has been solved, that the universe is teeming with robust, indestructible engines of life, perfectly capable of engineering their own survival against the hostile radiation of an alien sun. But science does not operate on hope. It operates on the cold, unforgiving friction between what we observe and what the fundamental laws of physics allow. And when we take the raw numbers from this exoplanet, the mass of the world, the proximity to its star, the violent volume of its biological exhaust, and feed them into our most advanced fluid dynamic and thermodynamic models, the equations do not balance. They do not just fail to balance, they actively contradict each other, creating a theoretical impasse that is tearing the astrophysical community apart. To understand the terrifying paradox we have uncovered, we must first look at the brutal limitations of our own vision. The James Webb Space Telescope is a marvel of optical engineering, but it is bound by the strict geometry of the transit method. When we say we are analyzing the atmosphere of this exoplanet, we are indulging in a dangerous oversimplification. We are not seeing the whole sky. We cannot see the boiling, superheated atmosphere of the dayside, locked in its eternal, searing noon. We cannot see the frozen, collapsing atmosphere of the nightside, buried under glaciers of its own condensed gases. We are only seeing the terminator line. We are observing the microscopic ring of twilight that separates the two hemispheres, purely because that is the only part of the planet's atmosphere that physical starlight passes through from our line of sight. Inferring the complex three-dimensional climate of an entire world from the two-dimensional shadow of its twilight zone is like trying to understand the sprawling, chaotic infrastructure of a massive metropolis by only looking at the silhouette of its outermost wall at midnight. We are extrapolating global biological saturation from a localized sliver of data. And the deeper we dig into the mechanics required to sustain that sliver, the faster the physics of the planet begin to break down into an unsolvable nightmare. The core of the paradox lies in the concept of atmospheric retention. For a planet to hold onto an atmosphere, especially one thick enough to support a global biological network and a supersonic wind system, it needs an invisible, impenetrable shield. On Earth, that shield is our magnetosphere. Deep beneath our feet, a massive ocean of liquid iron and nickel is constantly churning. Because the Earth rotates on its axis at a rapid 24-hour clip, the Coriolis force twists these convection currents of molten metal into immense, spiraling columns. This violent spinning liquid iron acts as a colossal geodynamo, generating a magnetic field that bursts out from the poles and wraps the entire planet in a protective magnetic cocoon. When the sun unleashes a wave of deadly high-energy solar wind, this magnetic field deflects the charged particles, allowing our delicate atmosphere to survive untouched. The math of the geodynamo is absolute. You need internal heat to keep the iron liquid, but crucially, you need a rapid planetary rotation to twist that liquid into an electromagnet. Without a fast spin, the magnetic shield simply collapses. This is where the physics of the tidally locked red dwarf planet collide with a terrifying reality. Because this exoplanet is locked into a synchronous orbit, its rotational momentum has been violently bled away by the immense gravitational drag of its star. It does not spin once every 24 hours. It barely spins at all, turning on its axis only once for every orbit it makes around the red dwarf, which could take weeks or months. Without that rapid rotation, the Coriolis force inside the planet's core is incredibly weak, practically non-existent. The molten iron might still be hot, it might still be circulating, but the fluid dynamics dictate that it cannot twist into the tight, organized columns required to generate a strong global magnetic field. The planet is completely naked. It is stripped of any meaningful magnetic defense, sitting at point-blank range against a magnetically unstable red dwarf that is known to lash out with stellar flares of devastating power. This triggers a catastrophic process known in astrophysics as hydrodynamic escape. When the high-energy extreme ultraviolet radiation from the red dwarf slams into the unprotected upper atmosphere of the planet, it does not just heat the gas. It violently severs the atomic bonds. If a photon of extreme ultraviolet light hits a water molecule floating in the alien sky, the immense energy shatters the connection between the hydrogen and the oxygen. Hydrogen is the lightest element in the universe. Once freed from the oxygen, the raw kinetic energy imparted by the stellar radiation pushes the hydrogen atoms past the planet's gravitational escape velocity. The planet's gravity is simply not strong enough to hold onto them. The hydrogen boils off into the eternal vacuum of space, lost forever. The heavier oxygen atoms are left behind, uselessly sinking back down to oxidize the planet's crust, turning the rocks a dead, rusty red. The mathematics of hydrodynamic escape are relentless. The equations dictate that the rate of atmospheric loss is directly proportional to the volume of extreme ultraviolet radiation emitted by the star, divided by the planet's gravitational binding energy. When we plug the telemetry from the James Webb into this equation, the result is catastrophic. The red dwarf is producing so much high-energy radiation, and the planet is sitting so dangerously close that the entire atmosphere should be physically blasted into space at a rate of millions of tons per second. Under this relentless stellar bombardment, an Earth-like atmosphere would be entirely stripped away in a matter of a few million years. It would leave behind a barren, sterilized rock, completely devoid of the reactive gases required to sustain life. Yet, the 99.7% signal mocks our equations. The heavy, complex shadows of dimethyl sulfide and other volatile biological markers are sitting right there in the data, saturated, thick, and undeniable. This forces a terrifying conclusion. If the atmosphere is being violently torn away by the star every single second, the only way the biological signal can remain so strong is if the life on that planet is actively manufacturing replacement gases at a speed that defies all known biological limits. The organisms in that twilight ocean are not just surviving, they are caught in an apocalyptic arms race against their own sun. They must metabolize and expel billions of tons of heavy gas into the sky constantly just to replace what the stellar wind is currently ripping away from the upper atmosphere. It is a biological engine running continuously past its theoretical red line, a global factory desperately trying to outpollute a hurricane of radiation. But this frantic, industrialized survival introduces a new, insurmountable barrier in the physical chemistry of the planet. A barrier of raw materials. Life cannot create matter out of nothing. To pump millions of tons of complex carbon and sulfur compounds into the atmosphere, the biological engine requires a constant, massive influx of raw chemical nutrients. On Earth, these nutrients are recycled through a slow, majestic geological process known as the deep carbon silicate cycle. Our tectonic plates constantly grind together, pulling carbon-rich rock deep into the Earth's mantle, melting it, and eventually throwing it back into the sky through volcanic eruptions. This tectonic recycling ensures that life never runs out of raw materials. It is the slow heartbeat of our world, but the mechanics of tectonic recycling require a very specific lubricant: liquid water. Immense oceans of water must seep into the fault lines of the planetary crust, hydrating the rock and lowering its melting point, allowing the colossal tectonic plates to slide over one another. If you remove the oceans, the friction becomes too great. The plate seize up. The crust locks into a single dead, unmoving shell. This is exactly what happened to Venus. When we look at the hydrodynamic escape models for our red dwarf exoplanet, we see a world that is hemorrhaging water into the void. As the extreme ultraviolet light shatters the water molecules and the hydrogen escapes, the twilight oceans are actively evaporating. And as the ocean levels drop, the planetary crust begins to dry out. The deep fault lines lose their lubrication. The immense friction builds. Slowly, inevitably, the tectonic plates of the alien world will lock together, shutting down the carbon silicate cycle forever. This is the ultimate paradox, the impenetrable barrier where all of our theories collapse into a dark, inescapable corner. If the biological engine is running hot enough to replace the atmosphere being stripped by the star, it must be consuming the ocean's nutrients at an astronomical rate. But because the ocean is also being blasted into space, the tectonic recycling system that provides those nutrients is shutting down. The biosphere is trapped in an impossible feedback loop. It is a bank account bleeding capital faster than it can be deposited, managed by a system that requires the very capital it is losing to survive. The mathematics reveal a merciless truth. The biology is acting as a massive, runaway catalyst for its own destruction. To protect itself from the star, it produces a heavy atmospheric smog. To produce the smog, it consumes the oceans and the deep sea minerals. By consuming the minerals while the water boils away, it guarantees the permanent death of the planet's geology. The harder the life fights to keep the atmosphere intact, the faster it drains the planet of the very elements required to sustain itself. It is not an ecosystem in balance, it is an ecosystem in the terminal stages of planetary asphyxiation. The deep frustration within the astrophysical community stems from the impossibility of resolving this conflict with our current tools. We are forced to watch this immense thermodynamic tragedy unfold through the tiny static-filled keyhole of an infrared spectrograph. We have no way to measure the exact depth of the alien oceans. We have no way to prove if the tectonic plates have already seized or if they are still grinding away in the dark. We have mathematical models that scream the planet should be dead, and we have raw telescope telemetry that screams the planet is overwhelmingly alive. There are theoretical physicists attempting to build new exotic models to bridge this gap. They hypothesize that perhaps the biology has evolved entirely beyond the need for a water-based carbon cycle. Perhaps the life forms have tapped into a form of slow, radioactive decay in the planetary crust, feeding directly on the thermal heat of the tidal friction rather than sunlight or oceanic upwellings. But these theories require a fundamental rewriting of biochemistry. They require us to accept that life can operate using enzymes and cellular structures that ignore the foundational rules of atomic energy exchange that govern every single organism on Earth. In the strict conservative halls of the scientific method, inventing new magical physics to explain uncomfortable data, is deeply frowned upon. We are forced to stick to the physics we know, and the physics we know dictate that this world is tearing itself apart. But as we stare at the conflicting equations, trying to reconcile the extreme mass loss driven by the red dwarf with the aggressive 99.7% biological saturation, a much darker, much colder realization begins to seep into the collective consciousness of the researchers. It is an understanding that cuts past the chemistry and the fluid dynamics, striking directly at the fundamental nature of observation in a universe governed by the speed of light. Space is not just a physical distance, it is a time machine. The speed of light in a vacuum is an absolute, unbreakable speed limit, clocking in at roughly 186,000 miles per second. In the context of a human commute, it is instantaneous. In the context of the cosmic void, it is a devastatingly slow crawl. The host star of our exoplanet is dozens of light years away. That means the light that the James Webb Space Telescope captured, the microscopic photons that filtered through the alien atmosphere and carried the chemical barcode of dimethyl sulfide into our sensors, did not leave that planet today. It left that planet decades ago. This introduces the concept of cosmic latency, a delay in the broadcast of reality that completely unravels our perception of this discovery. We are not looking at the planet as it exists right now. We are looking at a historical record, an archival photograph of a world as it was when those photons began their long journey across the interstellar dark. Normally, in astrophysics, a delay of a few decades or even a few centuries is utterly irrelevant. Stars burn for billions of years. Galaxies take hundreds of millions of years to rotate. A planetary system is usually a masterclass in slow geological stability. But this red dwarf system is not stable. It is a hyper-accelerated, violently dynamic environment. The biological engine is running at absolute maximum capacity. The hydrodynamic escape is stripping the sky at an exponential rate, and the tectonic cycle is crashing. We are looking at a system caught in the exact middle of a catastrophic thermodynamic tipping point. When you have a mathematical equation where one side is a violently evaporating ocean and the other side is an exhausted, overclocked biosphere desperately pumping out toxic gas, the entire system can collapse with terrifying speed. In geological terms, an atmosphere can transition from saturated to entirely stripped in the blink of an eye. The delicate balance in the twilight zone, the supersonic winds regulating the global temperature, the chemical smog shielding the ocean from the X-rays, all of it is resting on a knife's edge. This is the ultimate, terrifying barrier we cannot cross. The paradox in our models might not be a failure of our understanding of physics. The paradox might exist simply because we are analyzing a system that was already doomed. The massive, oversaturated biological signal we are seeing, the very signal that proved to humanity we are not alone, might not be the steady breathing of a robust alien ecosystem. Given the brutal math of the stellar radiation and the collapsing tectonic cycle, that 99.7% chemical spike could be something else entirely. It could be a desperate, violent bloom, a final planetary-scale overproduction of gas as the oceans hit a critical evaporation threshold. We are left staring at the telemetry, unable to reach out, unable to fast-forward the light, entirely trapped by the physics of the void, and we are forced to wonder if we are actually observing a living world or if we have just intercepted the final suffocating gasp of a biosphere. When the raw telemetry is finally fully processed, when the peer-reviewed papers are published, and the undeniable reality of this 99.7% alien biosignature is cemented into human history, the true casualty will not be our standard atmospheric models. The true irreversible casualty will be human ego. For centuries, our entire philosophical and scientific framework has been quietly propped up by a comforting, unspoken assumption, the anthropic principle. We looked at the Earth, its perfect distance from a stable yellow sun, its gentle 24-hour rotation, its protective, spinning magnetic shield, and its abundant liquid water, and we convinced ourselves that the universe was a delicate, fine-tuned machine. We believed that life was a fragile, miraculous anomaly, a rare and precious spark that could only ignite in the most pristine, peaceful nurseries of the cosmos. We called it the Goldilocks zone, not too hot, not too cold, perfectly balanced. This single absorption line in the infrared spectrum shatters the Goldilocks illusion permanently. It takes the concept of the delicate cosmic miracle and violently crushes it under the weight of raw, unfeeling thermodynamics. Because the biological engine operating in the twilight zone of that red dwarf is not existing in a pristine nursery. It is existing in a planetary slaughterhouse. It is a world stripped of its magnetic defenses, battered by unyielding extreme ultraviolet radiation, locked in a permanent screaming hurricane between a boiling desert and a frozen wasteland. And yet, it breathes. It manufactures. It actively saturates its sky with millions of tons of chemical armor. This forces a brutal recalculation of our place in the cosmic hierarchy. If life does not require a perfect, peaceful cradle to emerge, if it can take root and violently industrialize an environment that by all human standards is an active, lethal hellscape, then life is not a miracle. It is a thermodynamic inevitability. It is a fundamental, relentless property of matter. Give the universe a severe temperature gradient, a chemical imbalance, and enough time, and the physics will inevitably organize themselves into a consuming, reproducing engine. This realization violently strips away our special status. We are not the pinnacle of a carefully balanced cosmic equation sitting safely at the center of creation. We are simply one manifestation of a blind, mechanical imperative that infects the void wherever it can find the slightest foothold. And comparing our biology to the brutal resilience of that distant world is deeply unsettling. Life on Earth is soft. It is accustomed to the gentle shifting of seasons and the protective, invisible bubble of our magnetic field. We are like delicate greenhouse plants, cultivated in a quiet, climate-controlled room, suddenly looking out the glass and realizing that the frozen, irradiated wasteland outside is teeming with aggressive, hardened flora that feeds directly on the storms. But this profound shift in our understanding of biology unlocks a new, incredibly dark answer to the oldest, most terrifying question in modern astronomy: the Fermi paradox. The night sky is filled with hundreds of billions of stars in our galaxy alone. We now know through the statistics of the Kepler and Webb missions that almost all of them host planetary systems. If life is not a fragile miracle, if it is actually a robust, aggressive engine that can survive and adapt to the worst the universe has to offer, then the cosmos should be deafeningly loud. We should see the fingerprints of immense, star-spanning civilizations in every direction. We should detect the exhaust of Dyson spheres blocking out stars, the organized mathematical radio chatter of interstellar empires, the unnatural heat signatures of advanced, galaxy-wide engineering. And yet the silence of the void remains absolute. Until this single suffocating biosphere caught the eye of the James Webb, the universe presented itself as an infinite dead graveyard. For decades, we consoled ourselves with the idea of the Great Filter. The theory proposed that somewhere along the evolutionary timeline, there is a barrier, a filter so incredibly difficult to pass that almost no species survives it. We like to deeply believe that the Great Filter was entirely behind us. We assumed the hardest step was the initial spark, the chaotic transition from dead chemistry to the first self-replicating cell. We thought we had won the cosmic lottery, that we had survived the impossible mathematical hurdle, and that the quiet universe was simply our empty inheritance, a vast unclaimed frontier waiting for us to expand into it. The data from the red dwarf violently strips away that comfort. The chemical signal proves that the spark of life is not the filter. The universe is incredibly efficient at sparking life. It will ignite biology even in the most hostile, irradiated twilight zones of unstable stars. Therefore, the Great Filter is not behind us. The Great Filter is ahead of us. If life is common but advanced, spacefaring civilizations are entirely non-existent, it means that the universe routinely spawns these biological engines, allows them to grow, allows them to alter their atmospheres, and then ruthlessly exterminates them before they can leave their home worlds. Look again at the trajectory of the red dwarf exoplanet. It is a robust, highly active biosphere. It is fighting a magnificent planetary-scale war against its own sun. But it is a war of attrition dictated by cold, inescapable mathematics. The star is violently stripping the upper atmosphere. The oceans are evaporating into the vacuum. The tectonic plates are slowly drying out and are destined to lock. The biology is forced to consume its own planetary life support system just to maintain its temporary atmospheric shield. It is a biological network trapped in a sealed room, burning the very floorboards to keep warm, slowly, inevitably running out of oxygen. This is the hidden consequence of the discovery. It reveals the true horrifying nature of the cosmic filter. The barrier is not the creation of life. The barrier is the escape from thermodynamics. The universe is a trap. It allows life to emerge, but it places that life on ticking geological time bombs. A planet is a finite reservoir of mass and energy. A biosphere acts as an accelerating catalyst, consuming that reservoir to build complexity and maintain equilibrium. But eventually the math always catches up. The orbital mechanics, the stellar evolution, the geological friction, the environment inevitably shifts, and the biological engine is left stranded, unable to cross the vast, lethal distances of interstellar space before its local resources completely collapse. The vastness of the interstellar void acts as the final, impenetrable quarantine. For a century, science fiction has poisoned our expectations, feeding us the comforting delusion that once a civilization reaches a critical mass of technology or biological density, it simply builds ships and spreads across the galaxy. We imagined faster-than-light travel, artificial wormholes and warp drives, mathematical fantasies designed to help us cope with the sheer, crushing scale of reality. But the physics of the universe are not built for our psychological comfort. The energy required to accelerate even a small mass to a fraction of the speed of light is so astronomically high that it borders on the impossible. To move a biological population across dozens of light years requires essentially harnessing the total energy output of a star. A biosphere trapped on a failing planet cannot simply pack up and leave. As its environment collapses, its energy demands increase exponentially just to maintain baseline survival. The twilight organisms of the red dwarf cannot build generation ships. Every ounce of their metabolic energy is locked in a desperate second-by-second war against the stellar wind. They are pinned down by gravity and thermodynamics. And so are we. This is the mirror the James Webb Space Telescope has forced us to look into. The realization that biological isolation is an illusion, replaced by the grim reality of biological entrapment, completely rewrites how we must view our own future on Earth. We have spent the last 2 centuries acting as a massive, sudden catalyst upon our own planet. We have rapidly industrialized our atmosphere. We have dug deep into the crust to exhume millions of years of stored solar energy, the compressed fossilized remains of ancient biospheres, and we have burned it all in a geological fraction of a second to power our rapid technological ascent. Like the organisms in the twilight zone of the red dwarf, we have violently altered the chemical barcode of our world. If an alien telescope is currently observing the transit of Earth from 50 light-years away, they are not seeing the quiet, stable signature of a peaceful blue marble. They are seeing a chaotic, spiking anomaly in the infrared spectrum. They are seeing an atmosphere rapidly filling with carbon dioxide, synthetic fluorocarbons, and the aggressive exhaust of an industrial machine running at maximum capacity. We are running our own planetary engine deep into the red line. And just like the distant exoplanet, we are bound by the strict laws of planetary physics. Our Earth is larger, our Sun is more stable, and our magnetic field is currently intact. But the fundamental mathematics of the cosmic trap remain identical. We are a biological network consuming a finite reservoir of resources to build complexity, attempting to outpace the shifting environmental equilibrium of our host world. The energy we would need to leave our solar system en masse is the exact energy we are currently burning, just to keep our global civilization from starving in the dark. The James Webb discovery strips away the illusion of our permanence. We have always viewed human extinction as a theoretical possibility, a consequence of our own mistakes, a nuclear war, a failure to deflect a rogue asteroid, a localized climate collapse. But the 99.7% signal suggests something far more systemic and unavoidable. It suggests that planetary biospheres are inherently transient phenomena. They are like brief, violent chemical fires that flare up in the dark, alter the local atmospheric chemistry for a fraction of a geological second, and then permanently burn out when the fuel is exhausted or the local physics turn against them. This completely reshapes our understanding of deep time. In the grand mechanics of the cosmos, a civilization is not a permanent structure. It is a momentary latency. We are a brief flicker of organized information processing, trapped between the slow, dead geological past and the inevitable, expanding entropy of the future. The silence of the universe is not the silence of an empty desert. It is the silence of a minefield after the explosions have settled. The void is littered with the ghosts of thousands of biospheres that reached the absolute limit of their planetary engineering, stared up at the vast, unbridgeable distances between the stars, and quietly suffocated in the dark. We thought finding life would make the universe feel less lonely. Instead, it has made the universe feel infinitely more claustrophobic. We are no longer the only child in a massive, empty mansion. We are just one of countless inmates locked in separate, slowly shrinking cells, screaming into a void that is entirely too vast to carry the sound. We can see the chemical shadows of our neighbors, but we cannot reach them, we cannot save them, and we cannot learn from them before the light of their existence is permanently extinguished by the brutal, indifferent physics of their host stars. We are left staring at the telemetry, gripped by a profound, chilling clarity regarding our own timeline, slowly realizing that by looking at the violent, suffocating sky of a distant red dwarf, when you step outside tonight and look up at the cold, scattered diamond dust of the Milky Way, the constellations will appear exactly as they did 1,000 years ago. The physical geometry of the night sky remains unbroken, but the profound underlying meaning of that starlight has been permanently shattered. We can no longer look at the galaxy as a vast, open ocean waiting to be conquered by human engineering. The romantic era of space exploration, the comforting dream of a crowded, conversational universe, officially ended the moment those specific absorption lines resolved on the screens of our supercomputers. We now know exactly what is out there. The void is not an empty canvas. It is an infinite expanse of strict, localized quarantine zones. It is a dark, freezing architecture perfectly designed by the laws of physics to keep every biological spark violently isolated until it inevitably burns itself out. The red dwarf system we are observing with such desperate fascination is not a message of hope or an invitation. It is a mirror. It is a flawless mathematical reflection of our own inescapable predicament. We are standing on our own temporary rock, rapidly consuming our own finite reservoir of energy, staring across trillions of miles at another world doing exactly the same thing. Two brief, hyperactive chemical anomalies, separated by an unbridgeable gulf of space and time, screaming into a vacuum that does not possess the capacity to care. For all of human history, we have built our civilization on the arrogant premise of an infinite tomorrow. We construct towering monuments, we write sweeping histories, and we launch golden records into the dark, operating under the deeply ingrained assumption that the human story is destined to expand endlessly outward. But the mechanics of the cosmos offer no such guarantees. Thermodynamics does not recognize the value of our art, the brilliance of our mathematics, or our desperate biological desire to endure. The universe only provides a temporary ledger of energy. It grants a localized pocket of heat, a momentary chemical imbalance, and a ticking geological clock. And when that energy is finally spent, when the atmospheric shield inevitably collapses, the ledger is closed without ceremony. The 99.7% signal we are receiving right now will eventually fade from our instruments. Whether it takes a century or 100 millennia, the twilight oceans of that distant world will boil away into the vacuum. The deep tectonic plates will seize in the dark. The biological engine will suffocate under the relentless bombardment of its own sun, and that volatile red star will continue to burn for another trillion years, completely indifferent to the microscopic, desperate tragedy that played out in its orbit. The biosphere will be erased, leaving only dead rock and eternal silence. We are left with nothing but the ancient ghosts of their struggle. And as the reality of their doomed existence settles into our collective understanding, we are forced to accept the most terrifying truth the universe has to offer. We are not the destined protagonists of the cosmos. We are just another temporary disruption in the dust, operating our own fragile engine in the dark, waiting for our own light to finally reach the dead end of the void.